Alright, welcome ladies and gentlemen. This is 2B, force and acceleration. Trying to zoom in as much as possible as you can see it clearly. Give me a moment to focus. Oh, here we go. So the button says focus. Beautiful. I think that's way better. Hit button focus again. Okay. So we have this trial where Angela is on a very low friction skateboard while Blake is pushing her away towards a motion detector, and he's going to push her each time with different amounts of force. In trial 1, he pushes softly, then he stops pushing. In trial 2, he pushes slightly harder, then stops pushing. In trial 3, he pushes the hardest he can and then stops pushing. So at time T, it clearly says Blake stops pushing. There's no more force. So you can imagine how that comes into play later, but just keep at this point he is pushing. There is a force, no force. And so here, force, no force, if you want to kind of consider these two segments separated by this time T. Okay, so ideally, like, they're really trying to get us to understand how do we analyze this data, or how do we look at these graph sets. If you look at it, when Blake pushes harder, the slope, and so trial 3, he pushes the harder, softest, a little bit harder, the hardest. When Blake pushes harder, the slope of the velocity versus time graph, the slope, you can say what's happening to the slope. Pretty evident what's happening to the slope. It's increasing. And don't think we need to spend much time explaining on that. I hope you can see that directly from just how the graphs are going. I hope. If not, please see me, because we can fix that pretty quickly, that understanding. Now, as the velocity time graph, and this is what we've been saying in class all the time, since the slope increases, the acceleration is doing what? Well, increasing as well. And why can I make that statement? Because the slope on a velocity time graph, the slope of a velocity time graph equals acceleration. And here we have a velocity time graph. The slope equals acceleration. So if the slope is increasing, the acceleration is also increasing because of this statement here. So this is the understanding, and this is the application of this understanding. And so when Blake stops pushing, the slope of the velocity versus timeline becomes, so after this moment T, it all has the same value of slope. Here's different slopes. Low force, greater force, the greatest force. Of course, we just learned from the page before, the greater your force, the higher your acceleration. If you have your constant object, which is constant mass, Angela's the only thing on the skateboard. But as soon as that force goes away, all these cases have the same slope. The slope now becomes 0. And as the slope is now 0, this means that the acceleration is also 0, going back to this key fact that the slope of the velocity time graph equals acceleration. So the slope is 0, the acceleration is 0, and that makes perfect sense, because if there is no force, and we have the equation F equals m times a, if there is no force, there is no acceleration. It's not like we can't have mass. Angela, who's still there, actually has mass. It's not like she disappeared. You okay? Happy birthday, William. Okay? And so we're gonna continue on, and they're gonna challenge our thinking on the next set, which is part B, and saying that now imagine that he's gonna keep the force constant and then instead changes. He pushes with the same force every time, but in this case he's going to be adding on textbooks to Angela. So in this case, the mass is changing. Mass is changing. So we want to consider part B. Mass is changing. And so if it's the same force from 2A, as we learned, if this is the same force, if we increase the mass, the acceleration is going to decrease. And so let's just sketch a diagram of what we think it'll look like. And I don't know exactly because we have no real data, but I'm just saying that this could be what it looked like, because this can be the 2 textbooks and this could be the 4. It's 2 and 4. 2 texts and 4 texts. Because if the same force applied in all 3 cases, and that's the case, you're applying the same force, then of course as you increase the mass, you cannot accelerate as fast. The acceleration of the overall object or system is going to decrease because you're increasing the mass without increasing the force. The force is the same. And so the argumentation here, we're going to check this. The following statement is written to describe what will happen after the first 5 seconds when Blake is no longer pushing. After Blake stops pushing at time t, Angela will travel at a constant speed for a few seconds before she runs out of force. Then she will decelerate and stop. Well, what are we seeing here? Assuming no friction. I mean, we can assume that because it's a very, very low friction skateboard. Does the velocity ever go to 0? I hope you said no in a few seconds pause. If you said no, you'd be correct, because if this is the velocity on the y-axis, 0 is down here. I mean, Blake pushed and was accelerating and gave it accelerated to reach a velocity, then he stopped pushing, but then that skateboard now has that given velocity. The slope is now 0 after the force goes away. Just means that the force has went away, there's no more acceleration, but that just means that now you're going to travel constantly at that speed that you got to over this time period of which the force was exerted. And so after Blake stops pushing, Angela will travel at a constant speed, period. The rest of the statement is not true. There's no counteracting force. There's nothing that, it doesn't go to 0. It's just the fact that the velocity will not change until something else acts against her or against the motion. And so what are some cases? The velocity will not change. Velocity will not change until an opposing force acts against the motion, which is essentially Newton's first law. Like, there's nothing opposing her motion once she's getting moving. Her velocity will stay the same. Now, we can think of cases that's not true. In the real life, there is friction. There is air drag. There's air molecules hitting her that's going to slow her down, that drag. And so, or maybe she hits another object. But in the absence of those 3 examples, then she will continue to go. There's nothing stopping her. She'll continue to go at that constant velocity until an opposing force opposes her motion. And so here's a great checklist I want to go over here. That really, if you can go through this checklist, and I answered the question directly, yes, we answered it. You state a law of physics that is always true. Well, this is inherent in our response. We're using Newton's first law. Velocity will not change until an opposing force acts against the motion, according to Newton's first law. And so I can write that in. According to Newton's first law. I stated the law of physics is true. I connect the law of physics to the specific circumstances of the situation. Yes, it's explicitly state in this video, but of course you have to write it. And I use physics vocabulary. Did I use velocity? Did I use force? Did I use I mean, I've had to use these other words. So if you go through this checklist and give everything a check, then you're well on your way to getting a full-fledged valid response expected from the AP exam. Thank you for watching the second video, which I will upload shortly.